everyone and welcome. My name is Galen Arnold and today we will be discussing IR spectroscopy. Now, what is IR spectroscopy? IR spec is a diagnostic analytical tool used to confirm the presence or absence of an organic molecule by identifying the constituent functional groups. The instrument does this by sending a beam of high energy infrared light through a given sample. This input of energy causes the bonds between individual atoms to vibrate, resulting in stretches and bends. These stretches and bends can then be characterized by evaluating the spectrum generated by the instrument. The spectrum is built by comparing the percent transmittance, or how much energy is able to pass through the molecule entirely unhindered, against the wave number, which is the magnitude of the frequency of the infrared energy in inverse centimeters. There are two major regions in an IR spectrum: the fingerprint region, which illustrates minute components of a molecule. Peaks that fall under this category contain a wave number of 1400 or less. For our purposes, we will not be discussing the intricacies of the fingerprint region, save for one series of peaks at approximately 400 wave number, which we will get to later. The other major region is the functional group region, which contains all peaks above 1400 wave number. This region is able to identify different functional groups based upon how much energy the bond between two atoms is able to absorb before it either stretches or bends. Each peak, both the sharp and broad appearing icicle-like visuals, such as this one here, are indicative of a specific bond at a particular energy. Let's get into it. This next molecule is 1-hexene, with a pi bond or a double bond between carbons 1 and carbon 2. The difference between hexane and hexene is the presence of two sp2 hybridized carbon hydrogens and carbon-carbon bonds, each of which appear at approximately 3100 wave number and 1600 wave number respectively. Aside from that characteristic, the remaining four carbons are all indicative of an alkane, having peaks at 2900 wave number for an sp3 carbon hydrogen stretch and at 1300 wave number for carbon-carbon stretches. Next we have 1-hexyne with two pi bonds between carbons 1 and 2. Because of the higher percent S character, alkynes, or triple bonds in general, require greater energy in order to cause a detectable vibrational stretch. Therefore, an sp hybridized carbon of an alkyne will appear on an IR spectrum at roughly 3300 wave number, which we see here. Like 1-hexene, the rest of the molecule is essentially the same as the straight chain alkane, with the same peaks appearing as mentioned earlier. Moving on to the more interesting stuff, here we have a phenol, a benzene ring with an alcohol substituent. The two unique peaks with this molecule are the large and broad peaks centered around 3300 wave number. Normally seen closer to 3400 wave number, this is indicative of an OH stretch. However, due to the conjugated ring system, the observed wave numbers of all peaks are slightly reduced. The other peak of significance lies at approximately 1250, characteristic of a carbon-oxygen stretch. Normally observed at 1300 roughly, again, due to the conjugated ring system, the wave number is reduced by roughly 50 wave number. Pi bond stretches at 1500, slightly reduced for conjugation. You're going to have the aryl overtones at around 2000. Your CH sp2 your sp2ch stretches at roughly 3100, which again are going to be reduced because of conjugation. And yeah, that's essentially all. Those are all the major peaks that you will see in IR. Again, IR is a tremendously useful instrument for the identification of molecular functional groups. Although the sample is destroyed during analysis in this particular assay, it's a necessary sacrifice as the data generated from this tool are able to comprehensively identify the unknown molecule. Thanks for tuning in. Don't forget to like and subscribe. This next molecule is benzoic acid, a benzene ring with a carboxylic acid substituent. Carboxylic acids are generally fairly easily identifiable as they have a strong broad peak that ranges from roughly 3200 to 3600 wave number, and this accounts for all the OH stretches. There's some hydrogen bonding that is intrinsic to just carboxylic acid containing molecules. They're going to hydrogen bond to each other. There's a proton donating group and a proton receiving group in the oxygen, which is a part of this pi bond. And so additionally, the molecule is also going to have peaks at both 1700 right here and 1300. Again, that accounts for those carbon-oxygen double bonds and those carbon-oxygen single bonds. Our penultimate molecule is aminobenzene, a benzene ring with a primary amine substituent. In this case, we have two peaks between 34 and 3600 wave number, and this is indicative of a primary amine, as these have two hydrogens bonded to each nitrogen, excuse me. A secondary amine will have one peak, and a tertiary amine will have no peaks, and is actually entirely absent from IR, as there are no nitrogen hydrogen stretches whatsoever. Our next molecule is benzene. Don't worry, this is our last boring hydrocarbon. Benzene is a six-membered ring with alternating pi bonds. With a formula of C6H6, not only is each carbon sp2 hybridized, but the entire molecule is conjugated. Conjugation is one of the several minute intricacies of IR that affects the wave number. Typically speaking, conjugation reduces a molecule's wave number by approximately 50 to 60 wave number. The biggest takeaway from benzene are these small, seemingly insignificant peaks around 2000 wave number, known as the aryl overtones. This is a critical feature of this spectrum in all benzene-inclusive molecules, as they indicate the presence of that ring structure. Additionally, a strong peak at 1500 wave number is also observed here, which is illustrative of an aromatic carbon-carbon double bond. Finally, this last molecule is known as benzonitrile, a benzene ring with a nitrile substituent. Nitriles have a very identifiable peak at 2200 wave number. It's always very sharp, very intense, and pretty much actually very oftentimes looks like this. Aside from that, in this particular molecule, you will still have the same stretches that we've seen before, the same bends, the same